Okay, so good afternoon. This is perfect. Thank you very much for having the honor to conclude this conference. As a matter of fact, it's great that this presentation was done before my presentation, because that will illustrate actually what I'm going to say. So my background is in cockpit design, evaluation, certification, but also in control room design and the same. I worked with two large institutions in the past. Airbus is one of them. I was with somebody who you know at the flight test. And also I worked at NASA for many years, both in California and in Florida. I was chief scientist at Kennedy Space Center. So what I learned during all these years is the fact that, well, what should I say? I worked on automation most of the time, and also AI. What I observed that for a long time, people like me were there to build user interfaces. So you said user interfaces. But for me, the concept of user interface is a concept of the 20th century. In the 21st century, the user interface should be a component of the overall system and should be designed from the very beginning. So in other words, today we have the privilege compared to 20 years ago, or even more, to have digital media that can support the design of systems and then go quickly to human-in-the-loop simulations. So in fact, for that reason, we can do human-centered design. Before, that was extremely difficult because we had to wait that the full aircraft, we were doing flight tests. This is how I started, actually. But today, we can do flight tests virtually. The major, and I will come back on that, the major issue today is tangibility. Is the virtual world tangible enough in order to make sure that you are in a mature stage? You know, that's the problem. So what I want to show you is, you know, we heard many talks today on various kinds of artificial intelligence. I want to show you what I learned during all these years and talk about people, automation, artificial intelligence. If you look at this, you know, I take a model that is called the Rasmussen's model. James Rasmussen was a gentleman in working on nuclear power plants initially, and he tried to build a human model of nuclear power plant operators. And then we use this model in aviation. We use this model in many sectors. So in fact, there are three layers. The first layer is skill-based behavior. You know, you sense and then you act, like you bike. You know, this is... then this level was sent to the machine, automated, a long time ago. The first autopilot was in the 1930s. So, and then we incrementally improved actually this machine, if you like, and then we went to a second level, which is called rule-based behavior. That is more conscious. We were talking about consciousness. The first level is subconscious. The second level here is conscious, and then this level was automated on aircraft during the 80s with the FMS, and on top of the autopilot, if you like. And then we have a third level, that is the knowledge-based behavior, that is considered for quite a while now, and I put 2000, but we started before, you know, with cognitive engineering, a new discipline that emerged, and humanities and social sciences. So in fact, we went from basic automation to supervisory control to human-machine teaming. This is the evolution. And we start to talk about autonomy there. Probably we exaggerate at this point. But OK, now, as far as AI is concerned, here we can locate machine learning, deep learning, image recognition, speech recognition, all this kind of thing could be there, you know. And then it could be fully automated. A second level is case-based reasoning in AI. And the third level, I summarize that as the machine is a partner. It's not a tool at this point. You know, this is you cannot use that as a fork or a knife. You know, it's really a partner, and then you have to discuss with that. You know, this level. So in fact, you have two levels, two super levels, subconscious and conscious. Okay. So this being said, instead of talking about artificial intelligence systems, I prefer to talk about cognitive systems, in fact. I'm very pleased to see on your slides this cognitive thing. And in fact, socio-technical systems, this is what we use today as a term, evolution has gone from physical to cognitive and now to social. So let me show you. So before the 1980s, roughly, mechanical engineering was the king discipline in engineering. And then we moved to the 80s, 90s, where HCI, I forgot to tell you, there are the engineering disciplines and also the human factors discipline. And the human factors and ergonomics started after the Second World War. Between the 80s and 2000, we saw the emergence of human-computer interaction because the microcomputers emerged in the 1980s, and then we had to consider what we called cognitive engineering, the interaction with the computer, you know. Especially in the beginning, there was text processing. And then after, since the beginning of the 21st century, we moved towards HSI, Human Systems Integration. So instead of waiting that the system is finished and put on a user interface, then we consider the overall thing since the very beginning. And you had a very good demonstration before. So in fact, the problem is the complexity increases every day. Why? What is we can describe complexity in many ways, but one of the best description is you have nodes, links between the nodes, and the number of nodes and links increases exponentially. In fact, this is the point. So in fact, we see new disciplines coming, like digital engineering. We had an example. System engineering, and I call that there now artificial intelligence 2, because I started with artificial intelligence 1 in the 80s, that was symbolic. There was, machine learning was symbolic. And that we had neural networks, but that was very, the computers were not appropriate for that. And then today we start to see that we have a connection between artificial intelligence and system engineering. The agent of artificial intelligence are now called systems in system engineering. In other words, a multi-agent system is a system of systems. But we have done that for a long time, And so what we did is we moved from physical to cognitive and not today to social. This is our social cognitive, if you like. So in fact, I participate to a working group, if you like, a large working group. There are 20 universities in the United States. That's called AI for SC, SC for AI. Artificial Intelligence for System Engineering and System Engineering for Artificial Intelligence. And then the topic there is the human and machine multi-agent approach. The system of systems, if you like, but we can simulate, on computers. So I was in a meeting. Every year there is a meeting in September. I was there last September. And we developed a few things, like, this complementary approach between AI and system engineering, but also the human AI teaming. What is at stake there? And tangibility came back as a really major topic that we have to work on. I'm a scientist, so in fact, I'm interested in things that we have to explore. And here we need to explore more of that. And we need to have tools like the tools we saw just before my speech. So one of the things that is tremendously important today is the fact that we have to deal with the unexpected. You know, Fukushima, the COVID, and what do we do in these cases? Do we have the procedures? See. So in fact, AI for SC, I summarize what I said, agent versus system. You know, sometimes people say, well, a human cannot be represented as a system. But when you talk with a physical, with a medical doctor, you know, a physician, and he talks or she talks about the cardiovascular system or the cerebral system, it's not a machine, it's an organ. So that means that the system is a representation, in fact. So in fact, we take system as a representation. And that means that a human system can include a machine system, like the pacemaker, for instance, or my glasses. And a machine system can include a human. And then we start an ontology. You know, I have no time to describe the whole thing, but this is a first, attempt to give you what we do. A system is represented by a structure and a function all the time, like the heart, the structure, and the function is to pump the blood. And then the function and the system could be cognitive and or physical. So in fact, from there, we develop, you know, a language that we can use. And what I learned at school is that a system is an isolated entity that transforms an input into an output. But here today, it's not enough. We need to represent a system as a system of systems. A system includes other systems that works inside, and the system belongs to a bigger system. And then, as I said, there are functions and structures. The trick here is how do we allocate the functions on top of the structure? And then you can do that statically in the beginning, but it's better to do it when, dynamically. You know, that's interesting. And then if you put the system at work here, then you start to see what we call emergent functions, things that you didn't see in the beginning. You have to work on the system, you have to operate the system in order to discover these kind of things. And then further, you have to reintegrate this into the system. But this is also true, for the structures. You forgot to implement something, you know. And then all this, for me, is part of the new artificial intelligence that we need to better understand. So in order to discover this emergence in the system, I really remind you that the concept of emergence is really a property of complex systems, complexity. So in fact, you need to have criteria, principles like shared situation awareness, trust and collaboration. We worked on various kinds of things. Top, it means technology, organization, and people. And then we started to have this approach in a MMT project, Man-Machine Teaming project, that was led by from the DGA, led by Dassault Aviation and Thales. And I have no time to discuss this, but if you want to see more, you can go to our website, you will have the results. So how do we manage complex systems? Let's say complex socio-cognitive systems. And more than that, I talk about life-critical system here, because either aviation, aeronautics, and space and defense are life-critical. Okay. We use procedures for a long time. What do procedures do? They automate people. If you don't use the procedure, you can be sued or punished. So you automate human functions. And if you put this procedure into the machine, then you automate. So you automate machines. But this is for expected situation in a very well-defined context, or very well-defined context plural. And that defines a rigid world. When you get out from this context, then all this doesn't work anymore. And what do you do for unexpected situation? Well, you have to solve problems online. You have to solve the problem in real time. You know, this is left to the pilot, if you like. Then you need to have, you know, I had, when I was at NASA, during launches, we had always problems. And then suddenly when you have a problem, you have a myriad of people around coming, and then you have to coordinate all these very knowledgeable people. This is the same thing. Now we have some kind of AI with which you can interact, you know, but you need to be in a very flexible world. The rigidity here is not at stake. So in fact, we need to have something very flexible. And the tools that we are developing, that I call FlexTech, technology for flexibility, are extremely important to develop today. And I think AI has a good role to play there. So all this could be summarized as function allocation for the system. So in fact, the challenge is how do we go from this rigid automation that we know to the flexible autonomy where we want to go. And all this is not anymore single agent, a human in front of a computer, an interface, if you like. It's multi-agent. Yes. So in fact, the question I ask is, do we design tools or partners? This is the problem. So in fact, this is interesting because on the rigid world, we try to simplify. This is what I learned when I was a student, engineering student. Simplify the problem and solve it. You know, this is a you know, very rational thing, and you need to have a usable thing. Today, we need to deal with complex systems that you cannot simplify, in fact. You cannot simplify a human being. You have to get familiar with this complexity, and then you have to understand what is going on. This is why we need all these tools to simulate. Simulation is key. So in fact, the first thing that we used to know is reductionist. Now we have to deal with maturity of these tools that we are. And then NASA developed a long time ago, 30 years ago, maybe before, I think it was in the 80s, the technology readiness level, the TRLs. You know all this. But this is not enough. We need to develop human readiness levels, HRL. This one is the list of readiness levels, human readiness levels provided by the US Air Force. And then also organizational readiness levels. Because when a society is not ready, believe me, even if the technology is good, it will not go. And then more than that, I didn't put anything there because I think MIT has developed a list for machine learning, but maybe we should develop something there. How can we increase maturity? By considering this triptych, technology, organization, people, TOP, top model, we remember, with AI and data science on one side, and coordination, regulations on the organization, and on the people side, we have to deal with procedure following, whether it's automation or problem solving in the case of unexpected. Then when you deal with a complex system, and I go faster because I think the time is ticking, you know, the more you discover emergent functions and structure, the more the better the maturity is, in fact. This is one of the principles. So in fact, this is why it's very important to go in this direction. And consider the system as a living organism. It works, you know, it interacts. And then I want to finish on this. In fact, for a long time, in the technology-centered approach of engineering, we actually, if you take a manufacturer, whether it's Dassault or Airbus, or we have suppliers, and if you commit to the devices and think too early, then the design flexibility is dropping very quickly. And then you learn about the system, the ring curve, as you use it, in fact. You know, this is so now if you take this modeling and simulation approach that we saw before, you know, I make publicity for, for you. You know, if you take this, then you learn the green curve is translating to the left. And then you learn, but with the tangibility issue, okay? We should not forget that, okay? This is important. And then the flexibility, you know, the design flexibility can stay at a high level, and of course after that it drops. And then the commitment, the concavity is inverting as well. So in fact, this is interesting. This is a project we have with a company, Safran, on the maintenance of helicopter engines, distance maintenance. And then we worked on digital twin. You say virtual twin, but it's, we use the digital twin. And then this, what happens is this modeling and simulation in the beginning is used during the whole life cycle, in fact, of the product. And in fact, what it does is it enables to test the what if. You know, you have a complaint from someone in the north of Canada with a lot of powder snow in the engine, and say you test what it is. You know, this is an active documentation. You know, and you can improve this documentation, this active documentation, by inserting, incrementally integrating experience feedback as well. And then if you push a little bit further, then you can use it as a virtual assistant. This is another way. So, okay, I conclude. Sorry. So in fact, we have moved from this approach that is from tangible to virtual during the 20th century, you know, to another approach today, from the virtual to the tangible. We 3D print the hardware, in fact. We are doing this with and then I want to conclude on this. Why don't we talk about augmented social cognition instead of artificial intelligence? That's one of the things. So if you want to read more, this is, thank you.